Good morning, guys. Today we're going to continue our exploration of quantitative distributions. We're going to look specifically at what we call density curves and explore a special type of quantitative distribution called a normal distribution. But let's start with these density curves. We've seen situations like this, or histograms and things like that we've gathered from a sample. So if we think of this as a sample histogram, it gives us an idea about what's going on in the population, but we know it's not a true picture of the population. So if we want to use the histogram to kind of approximate what's going on with the population, we would be approximating with what we call a density curve. So if the sample looks like this, and then we say that that sample is representative of our population, we would expect our population to look something similar to that. So this would be what we call a population density curve. So when we talk about density curve, it's really just a population curve. Population curve. So in a population curve, in a density curve, we have kind of two rules that we need to keep in mind. First thing, everything is above the x-axis. And that should be intuitive because the density curve is just like the histogram. I'm never going to have a negative amount of anything. Because remember, histograms are just counting how often a certain value occurs. Now, I can have negative values on my x-axis, but I can't have counts of those values that are negative. So I can't have negative 3 people said such and such result, or you give a certain measurement. So everything has to be above the x-axis. So that's one characteristic of a density curve. The other characteristic is the entire area, total area under the curve is 1.0. And that just needs to come back to the idea that we need to be showing, since it's a population, 100% of the possible outcomes, 100% of the possible measurements that we got from that population. So those are kind of a couple rules for density curves, or population curve in this case. Now, the median and mean of a density curve is the same median and means that we've worked with before, but just a couple of ways that we refer to them. The median we know is the midpoint. It means we have the same number of values on either side of it. So when we're talking about median, it's the 50-50 point. Point, or the equal areas point. So if I calculated the area to the left of my median and to the right of my median, they would have the same number of values, they would have the same area. Now the mean is a little bit different than that. The mean of the density curve actually takes into account what the size of each of the values is. So we know that it's really, it's not resistant to those extreme values like we've talked about before. So the mean is more like the balancing point. So if our distribution was made out of, say, solid material, where we actually weighted the values, measuring what, weighted the values against what they are worth, it would be the point where we could actually balance the graph, or balance the distribution of the curve. So we've talked about some notation for sample distributions. We know that if we're dealing with a sample, then for the mean, we use the symbol x bar, and for the standard deviation, we use the symbol sx. When we're dealing with a population, we're going to change those up a little bit, and the mean is actually going to be this symbol right here. I can draw it a little better for you. That symbol right there, that is the Greek letter mu, or mu, depending on how you want to pronounce that. And its standard deviation, which is one we have looked at before, is going to be sigma. This is lowercase sigma, not the capital sigma you're used to from, like a lot of people think of with the Greek alphabet, or like when you're doing your summations in your algebra and calculus classes. So sigma is our standard deviation symbol, mu is our mean symbol. So if we're talking about a population, we're going to use these two symbols as a reference. If we're talking about a sample, we're going to use those two symbols. So the idea is it's more to just communicate what type of data you had to work with. Now we know that standard deviation for a sample and a population are calculated differently, so it really matters there. But for when we're talking about the means, it's really just, again, indicating what type of group, what type of distribution we're looking at, whether it's a sample distribution or a population distribution. All right, so now let's talk about this special kind of distribution, quantitative distribution, called a normal distribution. And I put it in quotations because that's the name of the distribution. It's what normally would happen. So when people were first kind of going through and looking at patterns of common occurrences, they would notice that they tended to take on the same proportions of results. So the fact that it occurred so often in so many different situations, for example, IQ scores, ACT scores, all these things where it's just you have large data sets and then they start all looking kind of the exact same when we graph it out from a shape standpoint and a spread standpoint, things like that. They just then went and started calling them the normal distribution. So that's why we name it the normal distribution. When we say normal, we're talking about a distribution, a quantitative distribution that fits these certain characteristics that we're getting ready to describe. All right, so the first one we've got here is the shape. So the shape of a normal distribution is going to be symmetric, and it's going to be single peak. Symmetric and a single peak. So it ends up looking something like that. Now that distribution should look very similar to, or familiar to you guys, because it looks similar to a bell. And that's what we're actually talking about. When you hear normal distribution, we're really talking about the bell curve that people often talk about. Grading a test on a curve, things like that. So the normal distribution is nothing more than the bell curve. So the shape we know is single peaked and symmetric. Okay? The mean is going to be the center of the distribution. Mean is going to be the center of the distribution. And since it's a population, that means we're going to use mu. When I get in a rush, my mu's will look like either of those. So both of those mean the same thing. Okay, so the mean is going to be represented by mu. We know that the standard deviation is going to be represented by sigma. Now, the standard deviation is really where this curve starts to take on the normal properties. And that is going to be what happens at one standard deviation. So at one standard deviation, if I look to the left and right, see how this graph goes from curving up to curving down? It's still increasing, but we changed which way it's curving right about here and right about here. Well, those 2 points, we call those the change in concavity. Change in concavity, whether it's concave up or concave down. You may remember those from your science courses. All right, so change in concavity, that's going to be at your one standard deviation mark. So the point where the curve changes concavity occurs one standard deviation from the mean. So if I were to go back one standard deviation, so if I go left one standard deviation, I'm going to get that concavity point. If I go right, I'll go plus one standard deviation, I'm going to hit that concavity point. So these are the one standard deviation marks from the mean. So that's kind of how we can measure a standard deviation, is if we've got the curve, the data graphed out, and we can look and see Where exactly it goes from curving down to curving back up, that's distance is 1 standard deviation. Alright, so now notation. Usually they'll say something like normally distributed with a mean of this and a standard deviation of that. But sometimes you'll see some texts that will say, give you something like this. So this just says the same thing. Normal distribution with a mean of this and a standard deviation of that. So I guess you could say, maybe if we had something like we were talking about IQs, we talked about how IQs are normally distributed. We might say IQs are normally distributed with a mean of 100 and a standard deviation of 15. So those are good examples, that's a good example of how you can write normal distributions. Some other characteristics that make a quantitative distribution normally distributed or normal is the frequency that each of the values kind of occurs, or the relative frequencies. So as you see right here, I have a normal distribution and I've broken it up into 1 standard deviation chunks. So we have the mean in the middle, and then we are 1 standard deviation to the right of the mean, 2 standard deviations to the right, 3 standard deviations to the right. So what it does is it seems to divide our graph into these equal width chunks, 1 standard deviation chunks. Now, if it's normally distributed, if the data says normally distributed, it's going to follow what we call the empirical rule, or sometimes you'll see it referred to as the 3 sigma rule. Right? Sigma is standard deviation, so 3 standard deviations rule. But most commonly, you'll see it referred to the 68, 95, 97, 99.7 rule. 99.7 rule. So the reason we call it that is because those 3 standard deviations are really divided into those proportions. So what does the rule say? The rule says that if I am within 1 standard deviation of the mean, so if I go 1 standard deviation to the right and 1 standard deviation to the left, 68% of my data should fall in that interval right there. So if it's normally distributed, that means it's single peaked, it's symmetric, the change in concavity is 1 standard deviation from the mean, then that means between those 2 concavity points, the change in concavity points, 68% of all of the data in the distribution will fall within, approximately 68% will fall between those 2 numbers. Well, if I were to go out another standard deviation, so say I have 2 standard deviations from the mean. Now I haven't covered 68%, we've covered a lot more of it. It's a whole lot of the graph we've got right here. We've actually covered 95% of the curve. 95% of the data is within 2 standard deviations of the mean. So you may hear sometimes people refer to, oh, well, they're 2 standard deviations away from the mean, so we can consider them abnormal. So if you want to consider somebody really smart, maybe their IQ is over 2 standard deviations from the mean. They're in that top 2.5% for intelligence, things like that. And then the final one is the 3rd standard deviation. So if we were to come all the way out to 3 standard deviations, we've now covered 99.7% of the group. So if somebody is more than 3 standard deviations above the mean, so say you were looking at somebody's height or something like that, and if heights were normally distributed, if they're more than 3 standard deviations, they're in this tiny little group up here. They're a really tall person. They're an exceptionally tall person. So that's what we're talking about when normally distributed. They fit this shape. They have this rule for standard deviation, and then the standard deviations divide into these very constant, very consistent proportions. So let's look at an example right here. In a normal distribution, that's what it'll be referred to. In a normal distribution, what is the probability of randomly selecting an individual whose value is within 2 standard deviations of the mean? So if I've got all the people that are represented by this graph, and I've got all of them sitting in a hat, all their names in a hat, not people in a hat, but the names, and I'm going to draw out one of those people, what's the probability that one of those names comes from the within 2 standard deviations mark? Well, the probability is that 95%, or 0.95. So 0.95 would be the probability. So another way you could kind of represent that is with that IQ thing we were just talking about. So if we said IQs have a mean of 100, mu is 100, and standard deviation is 15, if I was going to label this graph, go up 15, 115, go up another 15, 130, go up another 15, 145, and then going to the left, we're decreasing by 15. Going back again, going back again. So this is what it would look like with actual values in there. So if we had that IQ group where they're normally distributed with a mean of 15, it tells us that every 15 IQ points, we can see a certain chunk of the population. So in this problem right here, that 2 standard deviations, that 95% of people have an IQ between 70 and 130. That's the way we would read that. 95% of people have an IQ between 70 and 130. Now, the standard deviation, the 100's pretty set. Standard deviation, sometimes you'll see it 14, sometimes you'll see it 16 for IQs, but it's in that general range. But every normal distribution would look similar to that. So maybe if we're doing ACT scores, maybe in that case, the mean is a 21 with a standard deviation of 1.5 points. Something like that. So every time you go up 1.5 or 2 points or whatever the standard deviation is, that tells you you're going to have this specific proportion of values. And so these are the characteristics that make a normal distribution. They have these traits for standard deviation, those traits for shape, and they have these 3 sigma proportion breakdowns. We know it's always going to look like that every 1 standard deviation. All right, so because they are regular like this and they're normal, we can actually do a lot of calculations with any values that aren't just these whole number standard deviations. So we got 2 ways we can do that. One is using a table, and the other one is using your calculator. So let's first talk about how we can use a normal distribution table or a normal probability table to get some calculations or probabilities of some areas. First, I want you to look at the normal probability table that I've included with your note-taking guide. So pull that out, look at it. I have an excerpt of it here, but your normal probability table is going to look like this. And so, as you can see on this chunk of the normal probability table, there's a whole lot of decimals, and it says Z right here. Okay? So the normal probability table that we're going to be using, there's all kinds of them out there, but the one that we're going to use, and one that's the most common for the normal probability table, is all calculated on the left-hand side probabilities with less than Z probabilities. What do we mean by Z? Well, if we remember in the last section, we talked about how to calculate a Z-score. So Z-score, value minus mean over standard deviation. So really your Z-score was just telling you how many standard deviations above or below the mean you are. Well, why does it matter how many standard deviations above or below the mean you are? Well, if we remember, if we know the number of standard deviations above or below the mean, we know the specific proportions that are related to that. So that's why we really want to look at number of standard deviations. So what we actually have on that table is a standard normal probability curve. So if we see the words standard normal, that means you're dealing with a probability curve that has a mean of 0. So the center point is 0 and the standard deviation is 1. Mean of 0 and standard deviation of 1. So let's just that's what your Z-score is going to calculate. Now I should make comment, it should be kind of intuitive why that is the case, because if we do a mean of 0 and standard deviation of 1, if my center point my mean is x minus the mean minus mean is 0, so that should put your mean at 0. If my standard deviation is 1, and I go 1 standard deviation to the right, well, when I do the 1 standard deviation minus 0, you get a standard deviation divided by standard deviation, so your standard deviation is 1. So your standard normal curve means that instead of dealing with mean of 100, standard deviation of 15, or mean of 36, standard deviation of 2, we're now dealing with mean of 0, standard deviation of 1. It's just telling you the specific type of curve to work with. So this is how we can use z-scores, and then what we know about those probabilities, those predictable proportions with normal distributions, to be able to find really any value on a normal, the probability for any value in a normal distribution. Now, the curve that we work with, as I said, this is going to be a less than situation. It's always going to tell you this area over here. So if this is your z, the table is going to give you this area to the left every single time. That's the way our table. Some tables will tell you a right hand. They don't happen very often. Some tables may give you between values and stuff like that. All this stuff's predictable because we have set rules for how often each probability occurs. But what we use and what's most common is going to be this less than, or this left-hand area. All right, so let's talk about how to read through this. So I've got two examples up here. First one, we want the probability that we have a z-score less than 0.12. Okay? Probability that we have a z-score less than 0.12. So that just means that we had some value, some mean, and some standard deviation. We threw all that together, it gave us a 0.12. So now if we go to the table, well, if we notice there are 2 digits here, and our table is lined up in rows and columns. Now, our rows are our tenths place, and our columns are our hundredths place. Okay? So 0.12 has a tenths of 1, a hundredths place of 0.2, so that should be the area that we're looking at. So that should be the answer. Well, whenever I'm working these, I just want to draw it out just to make sure I have the answer that it's asking for. So if I draw my standard normal curve, just doing a quick sketch, we know our mean is 0, standard deviation is 1. 0.12 is going to be somewhere to the right. Okay. And we know that our table should always give us left side proportions. Now, does that look like it's over 50% based on that graph? Yeah. So this is what the table gives us, is what's to the left of that z-score, left of 0.12. And we can see based on the table 0.12 that proportion is 0.5478. So if I was going to answer that, maybe I'd say that 55% of people in whatever that group is have a z-score less than 0.12. Pretty straightforward right there. So when we have a less than situation, just read the table as it's written. Now what if we have a greater than situation? So if I'm looking at this one, z is greater than negative 0.21. Well, let's draw the picture. So if I draw it out, mean is 0, standard deviation is 1, negative 0.21 is somewhere over here. So before I even look at the table, I know, sorry, we want greater than. So I'm looking for all this stuff over here, right? This is greater than negative 0.21. So we know that this is going to be greater than 50%. So my answer should be greater than 50%. Well, if I go to the table and I find negative 0.21, negative 0.21, that's what the table gives me. Well, that's not over 50%, but on the graph we can see it's supposed to be over 50%. That's because the table only gives left-hand stuff. So remember, this is what you get from the table. From the table, we know that it's 0.4168. That's what we're getting from the table. But we don't want the left side, we want the right side. So in this situation, what we need to do to get the right side, go back to that original problem we talked about. Characteristic 2 for population density curve, the entire area under the curve has to be 1 or 1.0. So if the whole thing has an area total area of 1.0, well, the left side is 0.4168. How can I get the right side? That's right, we just subtract. So to get this answer right here, because it's a greater than situation, I'm going to do 1.0 minus whatever's in the table. Okay? 1.0 minus whatever the table says we're supposed to do. So 1 minus 0.4168 is going to give me 0.5832, I believe, which that does look good. Okay. So 0.5832 ends up being what we'll get on this one. So remember, the table is only going to tell us left side information. If you need right side information, like a greater than, you want to make sure you go in and subtract that from 1. So that's why I always like starting with drawing a picture, shading what I'm looking for, because it's a visual reminder of, am I looking for left side, which is the table? So when we have a less than situation, the table gives the answer. If I have a greater than situation, the table gives what we call the complement of the answer, so we got to subtract it from 1. And if I had a between situation, so say you said something like a z-score between 2 values, that's what it would look like. If it's between 2 values, graphically, it's going to look like, here's a z, here's a second z, and we want between. Well, how do we get that? Well, we know that if I took this whole area that the table gives me, and I took this whole area that the table gives me, so I take my area to the left of z2 and my area to the left of z1, and we subtract them, you're left with that portion in the middle. So if you have a between situation, that means you want to subtract table value for each z. So it's like treated as 2 separate problems, 2 less than problems, and just subtract it. All right, so that's how we can use the table. The table's nice, but honestly, because you're having to do so much bouncing around and reading which direction of the table, I really prefer to use the calculator for most of these. But this is good if you have a table and you don't have a calculator handy. All right, so we're going to jump over to the calculator real quick. I'm going to show you how to do all this same stuff and even more on the calculator with normal probabilities. Look at how we can get the calculator to help us with a lot of these normal probabilities. So here's a problem we have. ACT scores are normally distributed with a mean of 19 and a standard deviation of 6. So we see these key phrases: normally distributed, mean, standard deviation. All right, so if we look at a problem here, what % of students score between a 21 and a 31? we want to organize all this stuff. So it's a between situation. Like I was telling you before, anytime we deal with normal probability questions or percentages or areas, I always want to just draw a picture and get my information organized. So first thing I'm going to do is going to draw the normal curve, label what we know. Well, we know the mean is 19. We know the standard deviation is 6. So I just, remember, standard deviation tells you what the scale, the increments of your number line is. What else do we know? Well, we have some students scored a 21, some scored a 31, and we want to know the area between the two. So what percentage of this entire graph is between 21 and 31? Now, to answer this question, we could go to the table and calculate the z-score for 21, calculate the z-score for 31, look up each of those z-scores on our table, and then subtract the two areas. But I prefer to use a calculator because it kind of cuts out all that stuff and just jumps straight to finding between 21 and 31. So the calculator function we're going to use is called normal CDF. And I'll show you in a second on the calculator how we find that. But you actually, when you open the menu, you're going to see normal CDF, and then you're going to see a normal PDF. Never touch the normal PDF. We want the cumulative density function, so that's going to tell us all of these areas, all these values between 21 and 31. I think PDF stands for point density function, meaning it really just tells you the height of one specific point. So we want always normal CDF. We'll never mess with normal PDF. All right, and it's going to ask us for 4 things: lower, upper, mean, and standard deviation. Well, this is what those 4 things mean. Lower is just your left boundary value. Upper is your right boundary value. Mean is the mu, and standard deviation is your sigma. So in our graph right here, our problem, what's the lower or left boundary value of our shaded region? Yeah, it's right there. It's 21. What's the right boundary value? 31. The mean is 19. The standard deviation is 6. So we get all this stuff. We can key it into the calculator, and it should spit out the area between the two. So let's look at where we do that on the calculator. So I turn on my calculator. So this is when we're not working in the stat menu. We're going to work in the distributions menu. So second vars, so second variables, right above that, see where it says distribution. And just like I was saying right here, normal PDF, we don't want that. We want normal CDF. There's a lot of different distributions we'll use in here throughout the year. Remember, I told you 95% of the time we're in the stat menu. The other 5% of the time we're in the distributions menu. So normal CDF, you can see it asks for lower, upper, mu, and sigma. So our lower boundary, our left boundary was 21. Upper was 31. Our mean, our mu is 19, and our standard deviation, or sigma, is 6. Hit paste, hit enter, and I mistyped that in. See how you get a negative area? That tells you probably typed something incorrectly. Let's jump back in, normal CDF, and that's supposed to be 31. So between 21 and 31, there you go. So 0.3467. 0.3467 is the area under the curve between these two values. Or, in the context of this problem, 35% or 34.6% of students will score between a 21 and a 31 on the ACT. A lot faster than calculating a couple z-scores, looking them up on a table, and then getting your areas and subtracting them. So we just need to know what the left boundary and the right boundary are. All right, now let's look at another problem. What would a student have to score to be in the top 5%? So it's still same distribution, normal distribution, mean of 19, standard deviation of 6. What would a student have to score to be in the top 5%? Well, let's draw out what we have. We know our normal curve, we know our mean is 19, and we know that our standard deviation is 6, our increments are 6. Now, top 5% would be where on this graph? Would it be on the left end, the middle, the right end? Yeah, top 5% is going to be over here on the far right. So it's this far right tail. These are the highest scores. So this is somebody that scored really high. Now, when we have a problem that looks like this, it's a little bit different because now we don't know what the x value is. So this isn't one where we're looking for an area. This is one where we're looking for an x value. So when we see a problem like that, we're going to go do inverse norm in that distributions menu we just looked at. When you do inverse norm, it's going to ask you for area, mean, and standard deviation. Well, the area means the area to the left of the boundary value. Well, they didn't give us the area to the left of the boundary value. They gave us the area to the right. They said we want the top 5% or the top 0.05 area. So if we want to get this left area, we need to use that idea from of the density curves that says the total area is 1. So if I want this area over to the left, I'm going to have to do 1 minus the area on the right. So they get this area on the left side. I do 100% minus the 5% on the right, which is the 0.95. So the area that we're looking for is 0.95. Now, some of the calculators have newer programs, and they'll let you key in whether you have a right area, a left area, or a between area. But most of us are going to be using a calculator that it reads it like the table. It wants the left-hand area. The mean is still 19. The standard deviation is 6. So we're going to key this in to our calculator. So second distribution, inverse norm is option 3 right there. The area is 0.95, and if you don't trust your ability to subtract, you could type in 1 minus 0.05 and it'll calculate it for you. Okay. The mean was 19 and the standard deviation was 6. So when we calculate that, we get a 28.87. So the value, the ACT score that would have 5% of people higher than it would be 28.87%. Now, if we think about that, you can't really get a 28.87 on the ACT. So this is a situation, do I need to round down or round up? So let's just think, if I rounded down to 28, so if I came down here to 28, that means I'm not actually in the top 5% anymore. I'm actually a little bit below 5%. Maybe I'm at like 6% or something like that. Because if we move to the left, then this top percentage is going to get bigger. So for me to guarantee that I'm in the top 5%, I've got to round up. I've got to move into that interval. So when you're answering some of these questions in context, you may have to kind of throw out what you know about rounding and think which one's going to get the percentage that asks for. All right, so really you would say a 29 is what you would need to be in the top 5% of ACT scores. All right, so that's how we can do all that stuff on the calculator instead of with the tables. All right, last thing we'll talk about normal probability plots. Normal probability plots just give us an idea about the shape of a distribution, whether or not a normal distribution would be an appropriate model. Okay, so it's something we do on the calculator. We're not going to get into where the graph comes from, and I'll show you all in class how we can get that on the calculator. But it's going to make a graph that looks something like this. It's you have your data. In this case, we have our data over here on the left side, the vertical axis. And then you have how we made it normal. We normalized it on the horizontal axis. So where it can tell me my shape. If I see my number line right here, see how all my data is like packed up towards the larger numbers and it's more spread out towards the smaller values? Well, if we're spread out towards the smaller values, that's on the left side of the graph, that would be a left skewed distribution. In this case, see how my data is over here on the vertical axis and we're more spread out towards the higher numbers. So that means we're stretched out towards the higher numbers. That's the right side of the graph. That would be right skew. And see how my data is pretty consistent all the way across? That's where we would think maybe it's normal. Now we can also talk about whether there's a lot of fatness in the tails or not fatness in the tails, whether we're stretched out on the ends. But this is more or less what we're looking for. Wherever your data is at, whichever axis, if it's stretched out towards the low end, it's left skew. Stretched out to the right, large end, it's right skew. And if it's a perfectly straight line or close to it, then it's a normal distribution.